So this studying satellites, this is like fun stuff for a physicist. Now I've forced you to accept v squared over r, and let's just see what kind of fun stuff we can do with that. So a geosynchronous satellite orbits around the planet Earth in a circle. We'll call that little m. And it has a certain radius. And what we know is the time to go around once is 24 hours. And the trick is to put it way up high above the atmosphere so that it doesn't have drag from the air and fall down and burn up and all kinds of bad stuff. Okay, so this is really cool. As the Earth rotates, there's a satellite way up there just rotating faster in a bigger orbit, and it makes it also around over 24 hours. In actuality, the satellite is falling down. It's got centripetal radially inward acceleration. We could call that G prime. It's not 9.8 up there. It's much less because we're farther. Or well, okay, it's noticeably less. I think we'll calculate that in another example. But okay, find the altitude of such a satellite above the surface of the Earth. So, okay, to start off this problem, we have the force of gravity, big M little m over r squared, equals mv squared over r. Okay, I can just immediately write that down. There has to be a force pulling the satellite in there. Newton's force of gravity, he didn't bother to explain why he thought. He just rubbed it in everybody's face. There's still no explanation why that makes sense. But basically, it can't be any other power in the denominator besides r squared. He did kind of, like, at least use process of elimination. And this was just the simplest, most logical thing. He had no idea why, but observed a law that happens, and it moves in a circle. So we must have mv squared over r. And immediately we can say, aha, we dropped the m's. Okay. We can also say, since we're going around a circle, that our speed must be the circumference of the circle divided by the time to go around. Okay. Do you want to make a big mathematical mess? We're trying to solve for r. Oh. You sure can. You can cancel lots of r's. Okay. So here's what we do. We put v in here. T is 24 hours. It was an early homework problem to change that to seconds. So you should already have that written down somewhere. Okay. So we have g, big M. Yeah, we can cancel an r. So we'll put just one r equals v squared, which is 4 pi squared, r squared again, and t squared. And t is 24 hours. And I can actually cross that little r out, make it r3 over here. Oh, and I can start grouping terms. We'll assume you wrote stuff down. Okay. Yeah, there we go. Just right. Okay, I want everything away from the r's. R cubed equals big G times the mass of the Earth. Oh, we didn't. We're coming up on that. We have to do 24 hours in seconds squared, and then divided by 4 times pi squared. And we have to take that to the 1/3 power, or the cube root. Okay? That's a job for our calculators. So we'll just do that. You need the mass of the Earth, of course. Physics teachers know stuff like this, but you would have to look it up. It's about 6. If you like 6, you can just say it's 6. It's 5.97 times 10 to the 24th kilograms. A trillion times a trillion again. The plain old radius of the Earth, watch out, this is not the radius we need, but because we wanted the altitude, we're going to have to compare it, is 6.37, as best I can measure, times 10 to the 6 meters. Okay, so let's calculate. That G is like a 6.67. Got mass of the Earth. Oh my goodness, I need 24 hours. 24 times 3600. Okay, and then 6.67 is 11th times 5.97 to the 24th times my answer squared divided by 4 divided by pi squared. And then we take that to the power. No, I can't? What? Yeah, that's right. Okay. So I get 4.22. 1, 2, times 10 to the 7th. That sounds about right. Okay. So my altitude, though, above the surface, so this is always the distance from the center. I drew Earth as a dot. Isaac Newton invented calculus at first just for the purpose of proving that if you added up all the pieces of an object, even an oblong object with like the Earth with mountains or something weird shaped, I want to say grapefruit, but that's spherical. Bless you. But even like a gourd that has like elongated ends or something, you could just take it as the total mass at the very center of mass. So these r's are always distance from the center. So my altitude is r minus re. And look, this is going to be like 42 million minus 6 million meters. Okay. So about 3.6. Yeah, about 36. There we go. Million meters. Million. Or you could say 36,000 kilometers. They like kilometers for some reason, going to the moon and satellites and something, as though that's... Or we could do thousands of miles if we really wanted. And that's the altitude. And so it's pretty close. So on the test, I would love to ask questions where, okay, we're finding out maybe an easy one, how much time to orbit, maybe what's the speed of the orbit, the circumference divided by that time, and then we can get a little more serious and say, okay, what's our altitude, what's this, what's that. Yeah. For planet Earth. Oh, what's the big G? Is the constant 6.67 times 10 to the negative 11th power. It's on the equation sheets. Let's see. I put a little G prime, like you could plug in this radius. Oh man. It's approximately 10 times bigger, so gravity would be significantly weaker up there. Oh, I squared. Oh, why is it r cubed? Okay, it wasn't cubed at first. I started doing math on top of my math. It's v squared over here from the centripetal force, mv squared over r. I canceled my little m's because that's the mass in the satellite in both places. Good question. And then I squared v, so 2 pi squared is 4 times pi squared. Pi squared is almost 10, actually. It's close enough if you just want to use 10 instead of pi squared. And then I started doing math. Okay. Good. Okay, let's make that a complete video. Oh, because I have an r left over from my gravity equation. Gmm over r squared. Mv squared over r. Before I substituted v, I canceled one r from the denominator. Okay, so then I'm left with just gm over r. That's going to come up again. It's really fun. And then I set that equal to v squared, basically. So this whole term, 4 pi squared r squared over t squared, that is v squared. Okay, because it's around the circumference divided by the total time. Usually